First of all, I want to acknowledge my translator, my former student from Ukraine, Yulia Dzihora. She graduated a couple of years ago, and now she works for a Norwegian water company. Thank you very much, Yulia, and I hope you're able to listen today. And I also want to acknowledge Johannes Hieb. I met Johannes, as I said, about 30 years ago in the early 90s. And I had just become a professor of civil engineering, teaching water, wastewater, and waste at the Norwegian University of Life Sciences. Johannes was a green doctorate from Switzerland. And we met, and shortly after, we were initiating the European branch of the International Ecological Engineering Society. And we had as a goal to make all kinds of engineering greener. Our motto was, develop society with nature for the benefit of both. What are we doing today? We're developing society for the short-term benefit of man, sacrificing nature. Johannes and I have worked together on many projects, and many of them on wastewater. And early on, we were concerned about all the wastewater flowing out from our houses, from our cities and towns, polluting waterways, polluting groundwater. And where does this pollution come from? What does it contain? Well, it's the food we have eaten. It comes from agriculture products, goes through our body, and is discharged through the toilet, down the drains, to the wastewater. So it contains a lot of nutrients and other resources as organic matter that's actually misplaced in the water bodies. We thought early on this should go back to the agricultural domain, to silviculture, and so on. So we have worked with natural systems, constructed wetlands, different alternative toilets. We even tried dry toilets in apartment buildings, all with the goal of recycling resources back to agriculture. And today I'll give you an overview of what we have done, discuss a few approaches, and also we need to discuss what is the main need of regenerative agriculture. Are we hitting the target with our organic derived products from waste? We'll see. But I want to start, as Rick did yesterday. This is our little farm in Norway. We bought it 12 years ago. It's 3.5 hectares. 1.5 hectares is forest. My wife is the main farmer so far. I'm formally retired, but still work with the university a bit. And on the farm, we have 2 horses, we have chicken, we have bees, we have solar panels, and a very small market garden. You're all welcome to visit if you come to Norway. We are only just about half an hour from the main airport. The last project Johannes and I worked on together terminated in December of 2022. It's called CU Green, Sino-European Green and Smart Cities. Sino means that we had China on board. The project was centered around urban agriculture. But we derived all the resources for urban agriculture from urban waste. And the goal of the project was to minimize the input of resources, in this case, energy and water, to reuse the resources from wastewater and waste, in this case, nutrients, water, and energy, and thereby avoid discharging it to the waterways, and also reduce pollution or discharge of climate gases. This is the current system. Cities are receiving large amounts of food and energy and water, and in general, it's returned as pollution and also climate gases. This is a linear system. And this is the situation in most countries around the world. There's very little wastewater treatment that's sufficient. And the Commission in Brussels have recognized this. They have already put out requirements to remove organic matter, to remove phosphorus. Now, the new water directive will probably have stricter requirements. They want us to remove also nitrogen. They want us to remove organic micropollutants. That's important. And they hopefully also will initiate recycling. Probably that we should recycle 40 or 60% of the phosphorus. But it's still a lot of focus on removal. And removal of nitrogen, that is to turn the nitrogen back to nitrogen gas, which initially sounds good, but it costs a lot of energy. When we denitrify in our current treatment plants, we also emit, say, between 1 and 5% of nitrous oxide, which is almost 300 times more potent as a climate gas as CO2. We have other issues that also makes us focus more on recycling. And the war in Ukraine made the fertilizer prices peak. It's going a little bit down now, but the farmers are struggling. Farmers in Norway, their economy is going down, down, down. Their input factors in terms of fertilizers, pesticides, fuel is increasing. The farmers are in despair. And also availability is an issue. China is reducing their export of fertilizer, for instance. And for the fertilizer manufacturers, they're looking into resources that will be exhausted in not too many years. For phosphorus, the green curve here, you see we have about 250 years left with the current technology. Potassium that we mainly find in Russia and Belarus, it's about 90 years. If we go to zinc on the bottom here, you see it's only 17 years. That's an important micronutrient. And sulfur, 60 years. And then it's natural gas. What does natural gas have to do with it? Nitrogen fertilizer uses a lot of natural gas when it's produced. So we can expect those prices to still increase. And we have about 50 years left, according to Pettera Yensssen, a professor from the Swedish Agricultural University. So 15 to 250 years is what's remaining of the mineral resources with the current technology. So we have several motivations to recycle. It's the high fertilizer prices, it's the limited mineral resources, it's the production of end fertilizer that rely on natural gas and takes a lot of energy. We want, of course, to avoid pollution to our rivers and waterways. So, and we have the requirements from the EU that might also encourage recycling. What are the organic sources we can recycle? Well, it was interesting when I read the press release from the large Norwegian fertilizer manufacturer Yara in 2019. They estimated the fertilizer value of organic resources in Europe to 2 billion euros. And what are these resources? It's wastewater. And wastewater consists of gray water. That is all the water used for washing, showers, sinks, and so on. And in addition, you have the water, the excreta, urine, and feces. This is what we will concentrate on today. That's what we have time for. We also have organic household waste. We have different kinds of farm waste. We have waste from the food processing industry. All this can have resources that can be turned into both bioenergy and give nutrients for agriculture. And we in Norway have a lot of waste from aquaculture. Actually, in Norway, the discharge of organic matter from aquaculture by far exceeds the discharge from the country's population. But the government allows this to continue because we earn so much money from our aquaculture. Wastewater is a resource. And one person emits about 4.5 kilogram nitrogen, 0.6 kilogram phosphorus, and a kilo of potassium per year. Pretty good fertilizer combination. Also, 75 kilograms organic matter that can be turned into bioenergy and compost. If we think in terms of conventional agriculture, this amount can fertilize about 0.1 hectare at a low intensity application. On a world scale, we see that if we could recycle all our excreta, we could in Western Europe and North America supply about 15 to 20% of the current fertilizer, mineral fertilizer use. If you go to Eurasia, and Ukraine is a part of that, it's around 40. And in sub-Saharan Africa, we could substitute about all the current fertilizer use. This, of course, reflects that we use much more mineral fertilizer in West Europe than we do in sub-Saharan Africa. But conversion to regenerative agriculture will reduce the need for mineral-based fertilizers. Maybe, in some cases, totally eliminate the need. And maybe these organic fertilizers can supply, I think they can supply much more than 15, 20%, maybe everything. We'll see. Another interesting thing is that in the toilet waste, or in our excreta, urine and feces, we find 90% of the nitrogen, also around 90% of the phosphorus, and 80% of the potassium, plus more than 50% of the organic matter, and the majority of the pathogenic organisms. If we look a little bit more into detail on the wastewater fractions, we can see that urine is containing by far the most nutrients. Urine is the blue in this diagram. The brown or maroon, that is the fecal matter, contains much less. And the gray water, that's all the water except what comes through the toilet, contains maybe around 10% of the nutrients. So it's very minor compared to the excreta. If we go to the column to the very right, we see here that gray water constitutes most of the volume. And does any of you know how much we excrete per day in terms of urine and feces? Have any of you measured this? Probably not. But it's 1.5 liters on the average. Of course, it's more if you drink a lot of beer. In Norway, the average water use in households is 150 liters per person. So this means that 1% of the water, of the wastewater volume, contains 80–90% of the resources. We need all this water to transport the waste through our piping systems, to keep the speed up and the pipes cleaned. So if we had designed these systems today, I guess we would have done it differently. So if we're going to make organic fertilizers from, for instance, wastewater, we have some requirements, and EU have put out some requirements. You can see some references at the bottom of the page. And we have to be concerned about the content of pathogens. That is not very difficult to get rid of with the current practices we know. Heavy metals, that is also not the problem if we can collect clean excreta. But of course, in a large centralized system where we have input from industries, from roads and so on, it's more of a concern than in a small decentralized system where it's only households that's collected. Also, the content of organic micropollutants are more of a concern in the large systems than in the small systems where we have much better source control. And organic micropollutants, that is of concern today and will probably be a requirement to remove. That is pharmaceuticals, personal care products, flame retardants, as you have heard about PFAS, PFOS, and so on. This stuff we need to get out of the cycling, and we'll look into how. And first, we'll start with looking into large centralized systems. What can we do with our current systems? Because they will exist for decades. And then we'll go to the decentralized systems with source separation and look at systems from household and farm scale to city scale. As I said, we're concerned about removal today. It's very common to have biological treatment as a trickling filter, and you remove about 30% of the phosphorus in the sludge. If we go to a more advanced system, activated sludge with chemical precipitation, we can remove 90% of the phosphorus. We just talk about removal. And the problem with precipitating phosphorus, aluminum, and iron coagulants is that the aluminum and iron phosphates have a very low plant availability. So let's jump to Norway and GIA's treatment system outside Hamar in Norway. The larger treatment plants in Norway, and they have developed a new method for removing phosphorus. They precipitate phosphorus as struvite. Struvite is magnesium ammonium phosphate. The HIAS process, they remove 90% of the phosphorus. That means they meet their current requirement, that is 90%. But they remove 50% as struvite and 50% as organic phosphorus pellets. This is new. And struvite also contains some nitrogen. Struvite has been tested in Norway and other places. You see a couple of references here that you can read if you're interested. And it's a good slow release fertilizer. And struvite is now approved for use in conventional agriculture. And according to what I've heard but not read yet, it's also approved in organic agriculture in Europe, but this remains to be confirmed. What is required to precipitate struvite in a large system? Because it was easy, we could have done it a long time ago. Well, you need to concentrate the phosphorus. And in HIAS, they use a biological process to let the bacteria super consume phosphorus. They concentrate the phosphorus in the solution, and then they can precipitate struvite. And this is a groundbreaking process. It's probably the world's most compact biological treatment technology. They have avoided using chemicals. They have reduced the footprint of the system, and they have not increased the energy consumption of the system. Then let's move to nitrogen. I said nitrogen production required a lot of energy, 38 megajoules to produce 1 kilogram. That's as much as in 1 liter of diesel oil. If we can return nitrogen to agriculture at a lower energy cost, we probably have a more sustainable system. And how can we return nitrogen? When in the large systems, we already have ammonia stripping, but we need other things. Stripping can only take out 15%. Membranes, ion exchange, we have other systems. Algae-based systems are interesting. I'll come back to that. But a good system for recycling nitrogen in large-scale treatment plants have not yet been developed. Ammonia stripping, as they have in Norway's largest treatment plant, as you see a picture of here, produces ammonium sulfate, which they sell to Yara when they make fertilizer from it. But also ammonium stripping requires high concentration of ammonia. And this we only find in the reject water. The reject water is the water that comes from the sludge treatment. And that contains only about 15% of the nitrogen input to the treatment plant. So we can take out 15%. The rest is much harder to recycle. Before I leave the large systems, I want to look a little bit at energy and biochar production. Many systems, as you see in the picture here, it's their biogas system below. They produce biogas. That's not new. But microwave pyrolysis, as some of my colleagues, among others, are working on, is an interesting process to introduce at the treatment plants. And I think it should be introduced in future plants. With microwave pyrolysis, you can take sludge that cannot be used for other purposes. You can turn it into biochar and energy. And you can produce quite a bit of energy with this process. And biochar is also interesting. Julia worked on biochar, but this is not Julia's work I'm showing. It was another student that used coffee grinds to make biochar. And this coffee grinds resembled very much activated carbon. And activated carbon we use to sorb organic micropollutants. They have used biochar successfully in Sweden. We want to use it also to try to remove the organic micropollutants in our systems. And biochar has, of course, other positive effects. It's carbon negative. It is a good soil amendment, but we have to make sure that it has the right quality, and we should not cut down new forest just to make biochar because it's carbon negative. That may not be carbon negative. So do it with care. So we can summarize for the large systems. We should convert to struvite production, and we should facilitate nitrogen recycling. Recycling is currently limited to phosphorus, 90%. If we produce struvite, it can be available for agricultural production. But the other resources and micronutrients, we only can recycle in very small amounts. As I said, in larger systems, source control is more difficult. We need to pay more attention to heavy metals and to the micropollutants. I think large systems should investigate possibilities to produce soil amendment products from sludge, but it's also a challenging task. And in this task, they could consider to include microwave pyrolysis to get rid of the products that are not easy to recycle, that contains, for instance, organic micropollutants, because the microwave pyrolysis that will combust most of the organic micropollutants. So we have now looked at the large-scale systems, and we'll move to the decentralized systems with source separation that you can most easily do on a household scale. You can do it on a farm scale, but you can also do it on a city scale. I won't go too much into that, but it's a very interesting approach if we really want to do this and recycle from the large hubs of resources that the cities represent. I want to remind you, most of the resources is in the excreta, in the urine, and the feces. So if we had designed a wastewater treatment system or handling system today, I think we would have gone for source separation. We wouldn't have invented the water toilet and all these pipes that are so extremely costly, at least in Norway, to keep, to maintain and run and operate. We would have taken the toilet waste and we would have run it into what we call here on the diagram, nutrient and energy loop, where we produce nutrients, we can produce energy and soil amendment, and eventually food that we return to the society. We could also recycle the gray water. I won't go into that in this talk, but in the Sea Green EU project, we recycle gray water for irrigation, but also we made drinking water from gray water. I'll start with what I call community scale methods. And this is a demonstration system we have at our campus in Ås, Norway. We are using vacuum toilets for 24 flats in our student housing. The toilet waste or excreta is directly funneled or pumped to an anaerobic digestion system producing biogas. We can also add the organic household waste here. And what comes out of that is called digestate. And we have solid and liquid fractions that we turn into fertilizer. So when we burn off the biogas, we co-generate electricity and heat that is transported to a nearby greenhouse. We also produce CO2 when burning the biogas, and this is also funneled to the greenhouse to increase the CO2 content. This is a very special greenhouse. It's extremely well insulated, and it has a special vent system, so we can keep the CO2 in there and thereby increase the growth of the plants. The maximum growth we have at about 1200 ppm CO2 in the air, and in the air we breathe, we are around 400. From the liquid digestate, we produce liquid and solid fertilizer products. From the solid digestate, or what we filter off in this process, we compost that and produce compost or growth media. Struvite is difficult to produce in a large continuous process as they do in HIAS, but there are processes now, like the startup process they use in HIAS, that is commercial. That's an American process. But if you go down in scale, you can easily precipitate struvite in batch. And you see in the picture here, we have struvite in the bottom of this beaker. And we have tried to precipitate struvite with both magnesium chloride. We have used electrocoagulation, and we have used seawater. And you see the yellow curve here. It gives more struvite with seawater than with magnesium chloride. And magnesium chloride is expensive. So if you're near the sea, seawater could be an alternative. This is Melesse Esetu. He is one of our researchers. He's a very creative guy. He's heading our lab, and he did fabulous work during this Sea Green EU project. He has the biogas digestate in the bottle to the right. And in the beaker to the left, you see a clear liquid, and in the bottom, you see some green mass. That's algae. So Melesse has grown algae in the effluent from the biogas reactor. And when you grow algae in it, then you can take out 90% of both nitrogen and phosphorus, plus, of course, all the micronutrients. And you can grow different kind of algae. Algae can be used as green manure, fodder, and it can produce fat. Yeah, there are many, many possibilities. So I think using algae also in large scale might be a very promising option in the future that we should look more into. But we have talked about that we need to make high quality fertilizers. It cannot contain bacteria too much. It shouldn't contain organic micropollutants. So here where we have excreta from student housings, we know that we are below with heavy metals, below the requirements. We sand filtrate the digestate first. We get the clear liquid. When we have a clear liquid, we can treat it by UV light. And then we run the liquid through carbon filtration, activated carbon. And this is where I think in the future we can substitute with biochar. That's much cheaper. And then we grow the algae in a liquid that doesn't have pathogens of concern, and it doesn't have organic micropollutants. So the algae should be possible to certify for agriculture and food production. This is Melesse's little struvite reactor and his algae reactor. These methods are ready for upscaling. But they can be used in much smaller scale than you've seen in this large treatment plants like the HIAS plant where they produce struvite. This is interesting. Maybe you can do this locally in smaller groups. So from biogas digestate, we produce liquid fertilizer, and the liquid fertilizer, of course, contains all the nutrients, micro and micro. Struvite contains mainly phosphorus, and only 5% around is nitrogen in struvite. Algae biomass also absorbs all the nutrients, macro and micro. And then we make compost. So the system you see here is a decentralized, complete recycling system, can be used for one or more apartment buildings, a section of a city, a village, or a group of houses. It can also be used to sewer the whole city if you convert it to low flush toilets like vacuum toilets. But it's a technically fairly advanced system, and maybe it's expensive, but it's possible to do this decentralized with a system like this. And it's not more expensive than the conventional systems. We have made calculations showing that for a large development outside Oslo, 10,000 people, it's actually 50% cheaper in terms of investment, and also substantially cheaper in terms of operation and maintenance. And one of the reasons is that this can be built out in stages. You don't need to have the whole system in place before you can attach the first apartment. I won't go more into that, but it's extremely interesting to look at decentralized source operating systems also in cities. Then farm scale methods. If you're a farmer and you need fertilizer, why not build a sludge drying reed bed? That's in any textbook of wastewater treatment. But you can, instead of sludge, you can apply black water that you collect from your neighbors or from your own farm. You can also handle some of your manure in this system if you size it for it. And then you will have a clear, non-smelling solution coming out at the bottom of the system. And this you can apply as a liquid fertilizer in your field if that is appropriate. And you can also have a post-filtration stage in a small, simple filter to remove the organic micropollutants if you want to. And how should you apply this? Well, we saw some machines yesterday. I wanted to show this machine that a couple of colleagues developed in the 90s. It was developed to inject liquid fertilizer into the soil. And the liquid fertilizers we used was urine, it was processed black water, and it was also liquid composted manure. The reason why we wanted to inject it like this is that we surface apply it. You can lose 70, 89% of the ammonia because these liquids contain N in the form of ammonia mostly. It's also smell connected with that. But in this system, we shoot both seeds and the liquid, in this case, a fertilizing liquid, into the ground. We don't have anything that penetrates the ground. It's a ski, as you see here, that slides on top of the field and it shoots pulses down with the liquid and the seeds. When we did this, we had yields that was comparable to the yields with mineral fertilizer. And this was with much less power to pull. It was saving both operation time and power on the tractor. And we could do it easily in no-till systems. So could this machine be used for injection of compost extract, compost tea, or similar bioenhancing liquids? I have one concern because I work with vacuum toilets and how the vacuum affected microorganisms like bacteria. With the vacuum in normal vacuum toilets, they did not die off in large amounts. Here you have hydraulic pressure. How does that affect it? We need to test that, but they're pretty hardy guys. So most of them, but maybe the larger ones, if they were there, would be more effective. This needs to be seen. But anyhow, it's an interesting machine. And it can also be used to apply urine. And these pictures are from Sweden. Urine is the simplest way to get fertilizer if you are a farmer. Collect urine, store it for 6 months. That's what the WHO require, the World Health Organization. And it can be stored in pillow tanks on top of the ground. That's cheap. But you need urine diverting toilets. There are many of them on the market. I won't go into detail here, but some of them in porcelain and some of them, like a black and brown one here, you can build for a very cheap amount of money. urine has been tested in many trials, and this is one of the early trials in Norway, showing that also urine gave yields comparable to mineral fertilizer. So then we go to the household scale, and we move to Ukraine, Bogdan. And you sent me these nice pictures. I'm really looking forward to come down and see your biopots, because in the biopot, you can treat your wastewater. And at the bottom, you can have a clear, non-smelling nutrient soil. And this is how it happens. You have a pump and you spray it over a filter material, and then you treat the liquid. And if you filter through biochar, you can also here remove organic micropollutants. So you leave a little filter after the biopot, and the biopot looks nice, some of them are decorated. And the biochar you can produce at home. Bogdan is doing this. This is also Bogdan's creations. It's dry or compost toilets. And especially in rural areas, this is a good way to deal with sanitation. And this toilet has a urine diverting squat pan. So you can collect the urine if you want. And urine diversion, it reduces smell problems in such a toilet. And the feces you can add to the garden compost. And you see the garden compost here with the pretty hot. This is from our farm. My wife is smoking. So. But this is a way to give it a secondary composting and be sure you have destroyed all the pathogenic organisms. At last, I want to show you a dry toilet that we have tested in the EU project. It's a solar assisted dry toilet, and it has a solar panel on the side. And if you look at the figure at the bottom of the slide, the solar panel provides hot air, blows it into the composting compartment. It can also heat the toilet room, and it can drive 2 fans, also a fan that is extracting air from the compost compartment. In this toilet, we do not separate the urine, but the excess liquid is collected and it goes together with the feces into the secondary composting. And this was an urban garden in Denmark. They used the composted fecal matter and they had significantly higher growth and yields than with the regular practices in this garden. So then we'll sum up. It is possible to recycle both from large and small, in large and small scale, but it's more complex, more challenging in the large scale. We need better methods for nitrogen recycling to be developed for the large scale systems. And I think algae production in large scale can facilitate this and should be explored because you also recycle other nutrients. In source separated black water and urine, nitrogen phosphorus is concentrated. If you put in vacuum toilets or separate out the excreta in a city, you can truck this to the treatment plant if it produces struvite, if it has stripping, and then you can produce fertilizer. So I think applying source separation, at least in new buildings, that should be a requirement. And Sweden had it for a while, also as a requirement, some municipalities. But also in existing buildings and even in cities, this will facilitate recycling. And we need to make sure that we produce a high quality fertilizer. So removal of organic micropollutants is important. And that can be obtained using biochar of the right quality. And at last, but not least, and this is what I want to discuss with you guys, organic fertilizer products need to be tailored to suit the needs in regenerative agriculture. Maybe the needs for fertilizer aren't that high if you really can get the soil health and the soil food web to work, ideally where you live. But what can we do with the immense amounts of resources in terms of nutrients and organic matter that our cities and our homes produce? They should be recycled into some useful products, and agriculture can be one of the recipients. Thank you.
Щиро дякую за гарну доповідь, дуже насичено. Але ось таке питання. Дивіться, ми зараз знаходимо в місті Львів і йдемо по дорозі до ресторану, і дивлюсь, на будинках стоять старі ще факели для опалення, для освітлення міста газом, яке було в 19 сторіччі. Кожне місто, і в Європі в тому числі, мало потужні заводи по виробництву газу, які потужність вимірювалася в мільйонах кубів. Скажіть, будь ласка, яка прогрес сьогодні є у нас в порівнянні з тим, що мали по виробництву, тож біогаз був, тільки він використовувався для освітлення, в порівнянні з сучасними методами, сировиною і ефективністю? Дякую.
Well, biogas has you can say, at least the last decade, been implemented in more and more treatment systems. And it's used in various ways. It can be used in various ways. In Oslo, the capital of Norway, they are running buses from biogas. They do that in Sweden as well. If you have a gas distribution system, as some countries have, you can, of course, funnel it back to the houses. This is only dealing with what comes in the sludge fraction, in the organic matter in the sludge fraction. You don't recycle much nutrients this way, but it's a start. It's a good start to produce biogas from some of these organic waste resources. But you still have a sludge fraction that remains after you have burned off, you can say, the biogas from the organic matter that's easily volatile. And this has to be treated also. And this could be a resource for microwave pyrolysis, especially if you are concerned that it's contaminated. Or it can be an input to making the treatment plant also a soil producing factory, where they can use the inputs they have to produce garden soil for people and so on. But in terms of removing and recycling the large amounts of phosphorus and nitrogen, we're almost at stage 0 today. We need to improve the technologies. There is a technology now developed in Norway, as I showed you, that is actually commercial and can be implemented for those who want, and remove phosphorus. But remove and recycle phosphorus. For nitrogen, we are at stage 0 almost, I would say. There is no good method yet to both remove and recycle nitrogen. So what they look into in Norway is to, because they are afraid of the EU requirements, and the Norwegians, they want to be best guy in the class to comply to the EU requirements. So they're talking about now that they should pump the wastewater in the southeastern Norway to 16 large plants where they can do biological nitrification, denitrification. But they don't consider this holistically. What does it cost in terms of energy to pump wastewater kilometer after kilometer, to centralize it to a few treatment plants, just to let it go up into the air as N2 gas, but also producing nitrous oxides? So we are at a very critical point here. The EU will implement nitrogen requirements, and the response from the conservative wastewater community is we have to nitrify and denitrify, which is completely crazy in my opinion. We have to wait a few years and do this better. We could source separate also in the cities. In the house you are, they could put in vacuum toilets and collect the waste. Could be cheaper. Many things indicate that the source separation systems actually will be cheaper. and especially in the long run, because the environmental impacts will be less. I don't know if that was answering some of the questions, but
В нас є запитання із Zoom.
Okay, I'm also here on the conference in Lviv. So I will first say it in English and then I will translate it in Ukrainian. Thank you, Peter. It was a brilliant presentation, so informative. I enjoyed it all. And now I'm here and I have several questions, but I will start from the one. Could you please say me, does it require some special, I don't know, policy or documents to install this decentralized, big, relatively big wastewater treatment systems, as you told, for blocks, or it's like more simple procedure?
Дякую, Пітер. Була чудова презентація, багато питань, багато інформації. Моє перше питання: чи потребує така система якихось спеціальних дозволів в Норвегії? Мається на увазі система на будинок великий, багатоквартирний, або на декілька будинків?
yes, if I understand the question right, it's about the legal requirements you have if you want to install some of these decentralized recycling systems. And if we talk about the system I showed that we have at the campus of the university, this is something you can install in Norway if the municipality approves it. It's no more difficult formally than a conventional system where everything goes into one pipe. So, but the difficulty is that people in the municipality, in the consultant companies and so on, they are so hung up in the traditional ways of doing this that it's only a few municipalities now that are going for the new systems. But this is coming. We see more and more interest. So for the systems, the decentralized complete recycling system with biogas, with the production of fertilizer and so on, it's not really a legal problem. The problem is to convince the people in consultant companies, the municipality, that this will be a better solution for the future than continuing with the conventional system. And the conventional system in Norway will cost the Norwegian population a horrendous amount of money in the future. We have been screaming about electricity prices soaring. We have been screaming about fertilizer prices soaring. But when you hear that to upgrade and comply with the coming EU regulations, we have to invest in Norway an amount of money equaling $10,000 per head of the population. $10,000 per head. It's a horrendous amount of money. And we'll have another scream in a few years when they start to do this, if they don't start to think differently. For the small systems in your own house, a dry or composting or urine diverting toilet, if you handle this excreta yourself, you don't have to apply specifically in Norway. So that's easy. And you have, of course, to have a greywater system in that you have to apply for and has to be in compliance with current regulations. But there are, of course, regulatory hindrances in many countries, and in many places, the authorities also try to use this to avoid new systems because they're afraid that they haven't handled this before. It's easier to do as before, and yeah, it's a very, very conservative community. I've been working in wastewater for 40 years, and I use this metaphor that when I was a young student and got my first job, I thought, oh, 2, 3, 4 years, we'll see a difference. But now, after 40 years, I say that it's like if you were swimming in the middle of the Atlantic and then Titanic comes past. And you try to push this boat swimming. That's almost like what it have felt. But now we see that times are changing. We have so much more interest for these things now. 50% of Norwegian municipalities has come for post-educational courses to learn about this. And the EU project that we had has received an enormous amount of interest in Norway and other countries. So I think now is about time. And also, when we have the soaring fertilizer prices, farmers are screaming. There's so many incentives now to try to do this in a better way.
Дуже дякую вам, Петтере. В чаті багато людей дякують вам за презентацію. Їм дуже важлива інформація, яку ви надаєте. І маємо таке питання. Зараз ми маємо величезну екологічну проблему з викидом неочищеної стічної води в різних регіонах України. Чи є якісь технології швидкого реагування та переробки?
I'm not sure if I grasped the question completely, but you're asking for a water treatment system that you can use for small scale, for households, or is it large scale you're talking about?
І те, і інше.
Okay, well, it's in small scale, there is a quick fix. In small scale, I would recommend that you go to source separation. But you can also, most houses do not have a separate piping system, so everything goes out combined. Of course, you can use natural systems, constructed wetlands. That technology is available, and it should be available in Ukraine, I suppose. If you want to recycle, you can take the water after a constructed wetland and apply it in agriculture. It will be like the sludge drying reed bed, kind of, where you get the non-smelling liquid, where you have reduced the pathogens, and you can use it. We also have in Norway a lot of packaged treatment plants that is downscaled conventional systems with or without chemical precipitation. We have made investigations, and when you put a downscale large system into a box and set it next to a building, only 50% of them operate as they should. Because the different families have so many different practices, different water qualities. Some have no kids, other families have 6, 7 children, and the flow is varying. So it's, if you have space for a natural system, that's much more robust in case of a single house where you do not want to source separate. But if you do the source separation, you need to collect your excreta. If I were to do this in my house, I would try to install a dry toilet. If you do that right, like the toilet I showed you, it doesn't smell. People are afraid that the dry toilet might smell because that's your experience. You just have to construct it right in terms of ventilation. So that is a fairly simple engineering approach. And then you can handle this yourself if you are able to. Some people don't want to do this, but it could be organized. We have tried that in an area close to the university where a farmer collected the excreta from dry toilets, and he ran it through a secondary composting system and made a soil-like product that he used on his farm. So, and also if you want to install a tank, to dig and install a fiberglass tank is quite expensive. But in one of my picture on urine, you saw the pillow tanks. And these pillow tanks are very strong. And they can be folded. They can be taken under your arm. You can take it if you have a basement of the building, like the building you're sitting in, probably have a basement. You could take one corner down in basement. You could buy such a strong tank in reinforced plastic materials, put it there and connect it to a pipe that's accessible from the street so that the tank could be emptied at night. And if you had a urine diverting system, you could collect urine. You could use urinals for the men. You could use urine diverting toilets, so you could collect from women. There are also urinals now for women that you could install. Then this could go down into this tank. Or you can install vacuum toilets that today do not make noise like in airplanes. The new ones are as silent as a normal toilet. And the new dual flush vacuum toilets use very little water, around half a liter on the average. So it's possible to do this by source separation, even in cities, in a building like you have there. But there are also, I mean, treatment system, yes. You can buy treatment systems of various sizes from different companies, at least in Norway. Some of these are.
I have a commentary before the previous question. It could be unconventional situation in Sweden or like in Norway, sorry. But here in Ukraine, we have a situation when sewage truck, like for transportation, it could dump all the sewage sludge somewhere in the forest or in the river, just like illegally. And is there some quick approach how to fix it or like make it not smelling like this is like not disturbing the nature around it?
Well, I mean, if you illegally dump it, it's not much you can do, I guess. But if you dump it in a sludge drying reed bed, that is a fairly cheap in technology. You could have that. If you have it in the forest, you won't smell very much, and the reeds would also be there and reduce the smell. And we have thought about this in Norway, that a farmer that installs such a reed bed, he could have a small greenhouse that could be covering it, so that the bed he's discharging to could be covered when it's discharging if smell is a problem. And then you roll the greenhouse on wheels to a second compartment, because you always do compartments, and fill that one while the other one is maturing. So this is and you size them so that it can take 8 to 10 years before you start to empty them. And you can avoid the smell this way. I don't know if I answered your question fully.